The moment a car's rear wheel presses down on the asphalt, the road sinks by a few millimeters. The driver doesn't notice. Neither do the rest of us. The road looks flat. It stays flat. But this road isn't flat. It sinks, and it was built to sink. Now, to an engineer, this site is a nightmare, a crack, a maintenance report, the first sign of failure. But this engineer smiles, because that movement is their design. There's something beneath the asphalt. No engine is turning. No fuel is burning. It can't be seen. Yet it's there, and it's working. But what if, one day, it stops working? That's when the road that looks flat becomes the most dangerous road. Because this road stays standing by sinking. The engineers made it happen. They weren't afraid to start it. What they feared was this. One day, it might stop. A writing block isn't needed here, because you're asking for a direct translation segment by segment. Here's the faithful English version, preserving the meaning, tone, rhythm, and documentary style. Roads. Think about the one you take to work every day. The same stretch of asphalt in the morning, the same stretch again in the evening. It simply sits there, wearing down, cracking, and every few years being resurfaced. In budgets, it appears as nothing more than a single line item, maintenance costs. Yet every single day, thousands of tons of weight pass over it. When a truck brakes at a red light, its tires grip the asphalt, let out a brief squeal, and then that energy disappears into the air as heat. If you could touch that heat, it would burn your hand. But we never notice it, because within seconds, it dissipates and vanishes from sight. In reality, this is far from a small loss. The road network of an average city, if laid end to end, would easily stretch beyond the distance between two neighboring cities. And every single centimeter of those roads experiences the same cycle, every hour of every day. One wheel presses down, another lifts away. Imagine a single truck driving down a deserted highway after midnight. No sunlight, no wind. Yet its tires still press against the asphalt with exactly the same force. Solar panels produce nothing at that hour. Wind turbines stand still when the air is calm. But traffic never truly stops. And this is where the question that has fascinated engineers for years begins. Not how to discover a new source of energy, but how to stop wasting the force that already exists every single day. Perhaps the reason is simple. We've always looked at roads as if they had only one purpose. A road takes you from one place to another. That's all. For more than a century, we've designed asphalt for that single function. Electricity, water, and communication have always belonged to separate systems. But that way of thinking has already begun to change elsewhere. A roof no longer exists only to keep out the rain. It also generates electricity through the panels mounted on it. A window no longer exists only to let you see outside. It also helps retain the heat inside. Quietly, our infrastructure has begun taking on a second job. So what about our roads? Here comes the bold claim. Just a few hundred meters of highway could generate enough electricity from the traffic passing over it to power every street light in the surrounding area. No additional fuel, no dependence on sunlight, no need to build a single new power plant, just a material that transforms something already happening, the moment a tire presses against the asphalt, into electricity. When you first hear it, you might assume it's just another marketing slogan, a promise dressed up with words like green, sustainable, and the technology of the future, yet destined never to leave the pages of a brochure and enter the real world. That skepticism is completely understandable. After all, the world of energy is full of ideas that work perfectly in the laboratory, but never prove themselves outside it. But this project is not one of those ideas, because the physics behind it is far older than most people realize. In fact, it has probably been at work inside devices you've used for years without ever noticing. Think about a cigarette lighter. The instant your thumb presses the trigger, a tiny crystal inside is suddenly compressed, and the electrical charge created by that compression ignites the spark. That is exactly what we call the piezoelectric effect. Certain crystals and ceramics generate electricity when mechanical pressure is applied to them. We've known about it for well over a century. It's already used in lighters, microphones, sonar systems, and even certain medical imaging devices. But this is exactly where two questions emerge. Questions that change the fate of the entire idea. The first question is this: how do you take a system that fits inside a cigarette lighter and scale it up to a highway stretching for kilometers? The challenge isn't getting the crystal to generate electricity. The challenge is getting it to do so millions of times. Under pouring rain, buried beneath freezing asphalt, on road surfaces that exceed 50 degrees Celsius in the summer, inside a system repeatedly crushed by 40-ton trucks. The second question, perhaps even more difficult, is this: every application of pressure can generate electricity, but is every unit of electricity generated actually valuable enough to matter? How much power can a single moment of contact between a tire and the road really produce? Is it worth collecting, storing, and converting that energy into something genuinely useful? The entire project takes shape within the distance between these two questions. And while solving all of this, the road can never compromise safety. That's why this project is more than just a new energy technology. It is also a materials engineering challenge, an infrastructure challenge, and perhaps most importantly, a challenge of trust. Because people will only believe in a road that generates electricity when they can trust it to be every bit as safe as an ordinary road. No less and no more. So how does this system actually work? At first glance, the answer seems simple. A vehicle passes over the road, the surface flexes slightly, and electricity is generated. But for engineers, the real challenge begins after those three sentences. Because for that electricity to become genuinely useful, it first has to be collected, regulated, and stored in a reliable way. A few centimeters beneath the asphalt lies a layer you can think of as a sponge. But instead of absorbing water, it absorbs pressure. Inside it are thousands of tiny piezoelectric modules. Every time one is compressed, its shape changes by far less than a millimeter, converting that mechanical deformation into an electrical charge. As a vehicle passes overhead, the tire presses down on the asphalt. The modules compress and then return to their original shape. It's much like squeezing and releasing a small mechanical device in your hand to produce energy. Except here, it isn't your hand creating the motion. It's the thousands of vehicles traveling over the road every single day. The amount of energy produced by each individual event is quite small, and that's exactly what makes the system so fascinating. A single vehicle generates very little electricity, but when tens of thousands of vehicles pass over the same point day after day, those tiny amounts gradually accumulate into something meaningful. The electricity can't simply be connected directly to a power outlet. It first passes through power converters. Just as an uneven flow of water from a garden hose becomes a smooth, controlled jet after passing through a nozzle, the weak and irregular electrical output is transformed into a stable, usable form. It is then stored in batteries installed along the roadside. Only after that is it ready to be used. And this is where the system begins to serve two purposes at the same time. Streetlights, traffic signals, and electronic roadside message signs are already part of the road itself. Today, they draw their power from the city's electrical grid. But in theory, part of the energy they need could come directly from the traffic passing above them. And it doesn't have to stop there. That electricity could also be supplied to a nearby EV charging station, electronic displays at a bus stop, or, under the right conditions, even fed back into the city's power grid. That means, one day, while charging your electric vehicle, a small portion of the energy flowing into its battery could have been generated by the very road you drove over just minutes earlier. The road carried you first. Then, it powered you. Within the same journey, it performed two completely different roles. Now, imagine a busy urban intersection, a place where thousands of vehicles stop, accelerate, brake, and move again throughout the day. To a driver, it's just another intersection. But to an engineer, it's a natural source of mechanical pressure operating non-stop from morning until night. That's why not every road is the same. Some locations are far more valuable than others when it comes to generating electricity. And that difference changes the choice of materials as well. Rigid ceramic-based modules can produce more electricity, but they are also more prone to cracking. Flexible polymer-based modules deliver slightly lower efficiency, yet they are far more resistant to temperature fluctuations, moisture, and the fatigue caused by continuous loading. That's why engineers don't ask, which material is the best? They ask, which material is the right one for this specific location? The answer may be different for a busy but sheltered toll plaza, different again for a long highway exposed to the elements, and different once more for the entrance to a seaport. In other words, every section of road is engineered individually, according to the conditions it will face. But there's another important detail. This system is not intended to replace the existing energy infrastructure. The electrical grid is still there. Solar panels remain on rooftops. Wind turbines keep turning. Piezoelectric roads are not an alternative to those technologies. They are a new layer, one that captures a source of energy that has been completely wasted until now and adds it to the system. And over time, engineers began to realize that this technology was doing more than just generating electricity. That's where the real surprise emerged. Imagine a time close to midnight. A maintenance worker stands beside the highway, using a flashlight to open an access panel beneath the asphalt. In the distance, the headlights of a passing truck cast his shadow across the road for a few brief seconds before darkness quietly settles over everything once again. Normally, beneath that panel, you would expect to find nothing more than ordinary electrical cables and junction boxes. But this time, one small display catches the eye. A simple screen showing in kilowatt hours the total amount of energy generated throughout the day by the vehicles that have passed overhead. The worker glances at the display. At that exact moment, another truck rolls across the road above. The number on the screen silently ticks upward. The truck continues on its way. The driver doesn't feel a thing, yet without even realizing it, the vehicle leaves behind a small trail of energy. For a brief moment, the worker looks up at the dark highway, the hundreds of vehicles that have passed over it. They didn't just travel from one place to another. They also kept this system alive. In that moment, the road no longer looks like ordinary asphalt. It feels as though an invisible machine has been working beneath it the entire time, without ever stopping. The worker closes the access panel and walks back to his maintenance vehicle. He starts the engine. A few minutes later, his own tires begin feeding the very same system operating beneath the road. But the quiet numbers climbing on that display are not the surprise engineers ultimately discovered. The real surprise lies far beyond what the screen can measure, and it only reveals itself when you ask a simple question. If this system works in such a straightforward way, why isn't it already beneath every road? If the idea seems so logical, the first question that naturally comes to mind is this: why don't we see it on every highway yet? After all, we're not creating a new fuel. We're not discovering a new source of energy. We're simply trying to convert pressure that already exists into electricity. And the technology itself is far from purely experimental. Pilot projects have been operating in different parts of the world for years, collecting data under real traffic conditions. Most people assume the problem is the amount of energy produced. But that's not the real issue. The greatest challenge for engineers isn't getting a crystal to generate electricity. It's getting that crystal to do it reliably, continuously, and without failure for decades. And that turns out to be a far more difficult problem than it first appears. The first obstacle: durability. A highway is a living structure that carries millions of vehicles every year. Piezoelectric modules must withstand that relentless, repetitive load for years without losing performance. In the earliest pilot projects, that proved far from easy. Some modules cracked, others were damaged by moisture. Picture an engineer holding one in his hand. A small module, recovered from beneath the road just a few months earlier, its edge marked by a faint crack. He lifts it toward the light, slowly turning it, searching for the exact point where the fracture began. Every day spent outside the laboratory teaches that tiny component something new. That revealed an important truth. Improving the system wasn't simply about generating more electricity. It was about designing a structure capable of operating reliably for years. Because replacing a module buried beneath the asphalt isn't as simple as changing a light bulb. It requires closing the road and managing traffic around the work. So engineers change the design. Instead of building one large, integrated system, they developed independent modular units. If one component fails, only that module needs to be replaced, rather than dismantling the entire system. Much like a single dead pixel on an LED display doesn't require replacing the entire screen. New generation polymer materials have also helped address the problem. Compared with ceramics, they are more flexible and far more resistant to impacts and temperature fluctuations. But even after durability is solved, another question remains: is it really worth installing? The second obstacle: cost and efficiency. A section of road equipped with piezoelectric modules is still considerably more expensive than conventional asphalt. And the amount of electricity generated by a single vehicle is relatively small. It was never designed to power an entire city. That's why the real question isn't, is it expensive? The real question is, where can it pay for itself the fastest? Because not every road produces the same amount of energy. A quiet residential street cannot compare with the entrance to a busy seaport, where thousands of trucks stop and start every day. Locations where vehicles brake and accelerate, such as traffic lights and toll plazas, can deliver a much faster return on investment. That's why the first deployments are concentrated in places where traffic is both heavy and predictable. Success doesn't depend on what a single vehicle generates. It depends on how efficiently the movement of thousands of vehicles throughout the day can be captured. But even if the technical and economic challenges are overcome, one final obstacle remains. Perhaps the most important of all: trust. No public authority wants to transform a road used by millions of people with a technology that hasn't been thoroughly proven. Because here, there is no margin for error. A failure at a power plant may cause a blackout, but a failure on a highway can directly affect human lives. That's why piezoelectric roads are tested first in laboratories, then in pilot projects, and finally, under real traffic conditions for years. Every deployment measures more than just energy production. It also evaluates safety, durability, and long-term maintenance costs. This slow pace doesn't mean the technology is weak. It shows how engineering actually works. Major infrastructure is proven first, then it earns trust. Only then does it become an ordinary part of everyday life. And piezoelectric roads are now traveling exactly that path. The greatest amount of energy isn't generated where vehicles maintain a constant speed. It's generated where they slow down or come to a stop. That's because during braking, the pressure a tire applies to the asphalt is both significantly greater and far more sudden than it is when a vehicle is cruising steadily along a straight road. That's why engineers are no longer focusing on covering entire highways. Instead, they're targeting specific locations, just before traffic lights, at toll plaza entrances, on deceleration lanes, at parking lot exits, and in school zones where vehicles are required to slow down. At first glance, this may seem like a minor engineering detail, but in reality, it changes the entire logic of the project. Instead of covering kilometers of highway from end to end, engineers identify the city's highest energy locations and equip only those areas. This approach dramatically reduces the overall cost while keeping the amount of electricity generated at nearly the same level. Some engineers call this smart location selection. Don't cover the entire road. Identify the part of the road that works the hardest. Picture the monitor on a traffic engineer's desk. A map of an intersection fills the screen, with every location marked in a different color. The areas closest to red indicate where the hardest braking events occur throughout the day. After weeks of collecting data, that intersection has been transformed into an energy potential map. Only the locations with the highest scores are considered worthy of the costly installation process. But this engineering decision has another important consequence. The real opportunity doesn't come from one massive investment. It comes from many small, distributed ones. A city doesn't have to equip every road overnight. It can begin with a single intersection, a school zone, or the entrance to a hospital as a pilot site. If the system pays for itself within a few years, the next location follows. If it doesn't, the data is reviewed and another site is selected instead. This approach avoids the trap that large infrastructure projects often fall into. Instead of trying to do everything, everywhere, all at once, it follows a simpler philosophy. Start where it delivers the greatest benefit, measure the results, then expand. That philosophy has also attracted the private sector. A highway operator whose revenue once came solely from tolls can now transform that same road into a small-scale energy producer. Public-private partnerships become especially valuable here. Rather than covering the installation costs alone, a municipality can partner with an energy company and share the electricity generated by the system. But what about the environment? Manufacturing piezoelectric modules requires both energy and raw materials. That means the system doesn't begin its life with zero environmental impact. Like solar panels or wind turbines, it carries an environmental cost during production. But once installed, it operates silently, consuming no fuel and producing no emissions. Over the years, the environmental cost of manufacturing is gradually offset by the steady stream of clean energy the system continues to generate. What this means for you is actually quite simple. Every moment you walk, drive, or stop is no longer completely wasted. The city begins collecting something from your movement without you noticing and without requiring any extra effort from you. But beyond the engineering calculations, something unexpected begins to happen. In some early pilot projects, researchers observed that once drivers learned they were traveling on an energy-generating road, many of them began driving more carefully and more smoothly, as if they felt they were contributing to something. Instead of braking hard at the last moment, they tended to slow down in a more controlled way, creating a positive side effect for both road safety and energy generation. Whether that effect is lasting or simply a temporary result of the technology's novelty, however, remains unclear. Even researchers have yet to reach a consensus. Some believe the awareness will fade after a few months. Others argue that regular feedback displays could make the effect more permanent. In reality, this debate extends far beyond piezoelectric roads. Studies have shown that when household electricity meters are placed somewhere visible, people tend to reduce their energy consumption. The principle is the same. When people can see the impact of their own behavior, they naturally make small adjustments. A simple roadside display showing, "This is how much energy has been generated today," could turn out to be one of the least expensive and most effective design decisions of all. And now we arrive at perhaps the least discussed, yet one of the most practical layers of the technology. Piezoelectric modules don't just generate electricity, they also measure the pressure applied to them, along with the duration and intensity of that pressure. In other words, the same road can monitor traffic density, average speed, and even vehicle weight in real time, without requiring municipalities to install separate sensor networks, additional cameras, or entirely new infrastructure. For a traffic engineer, that's an extraordinarily valuable source of data. Knowing how many heavy vehicles pass through a particular location, in which direction, and at what time of day can improve everything from traffic signal timing to the detection of overloaded trucks. For example, an overloaded truck crossing a bridge is often discovered only after an accident or during a random inspection. But a piezoelectric section of road could automatically estimate the truck's weight the moment it passes overhead and instantly alert the appropriate authorities without the need for additional cameras or dedicated weigh stations. So what began as the idea of a road that generates electricity gradually evolves into something much more. A road that monitors its own traffic and understands its own condition. Not through a separate, expensive system, but as a natural extension of the very same technology. Imagine a city 10 years from now. One of its main intersections no longer directs traffic alone. It may also be powering the surrounding streetlights, traffic signals, and perhaps even the nighttime lighting of a nearby park. The charging station where you plug in your electric vehicle could be drawing its energy partly from solar panels, partly from the city's electrical grid, and partly from the very road you drove across just moments earlier. A small icon on the charging screen might even show how much of that day's electricity came directly from the road. A school could power the sidewalk lights outside its entrance using the energy generated by the deceleration lane in front of it. Every morning and afternoon, as parents slow down to drop off their children, they would be contributing a small amount of energy without even realizing it. A busy seaport entrance or a border checkpoint could collect enough energy from the weight of passing trucks to operate its own security cameras and barrier systems. One day, city planners designing a new intersection might evaluate not only its traffic flow, but also its energy potential. Just as we already assess whether a piece of land receives enough sunlight for solar panels, tomorrow we may evaluate whether an intersection experiences enough traffic to justify a piezoelectric installation. None of these scenarios is a guaranteed future, but they are all possible futures. And that possibility is being tested right now, carefully and step by step, in laboratories and on a handful of pilot roads around the world. Perhaps the most realistic outcome is this: the technology won't transform your life overnight. Instead, over the years, it will quietly become an invisible part of the city itself, much like the sidewalk beneath your feet today, whose construction you probably never stop to think about. One day, an electricity-generating road may no longer be considered news at all. It may simply become another ordinary piece of infrastructure. We began with just a few millimeters of compression beneath the weight of a passing truck. A tiny movement. Quiet. Almost impossible to notice. But perhaps that's the real point. Until now, we've always thought of energy as something we have to produce. Build a power plant. Install solar panels. Spin a wind turbine. Always creating something new from scratch. Yet this project asks a different question. What if the energy is already hidden inside the things we do every day? What if every step we take, every time we brake, every rotation of a wheel is actually an invisible resource, simply waiting to be used? Once we stop seeing roads as something that only wears out, consumes resources, and demands maintenance, and begin seeing them as something that can also give something back, what else in our daily lives might we have been misunderstanding? Perhaps the most remarkable part is this. The idea wasn't born from inventing a new technology. It came from questioning an old habit. The piezoelectric effect has been known for more than a century. The material didn't change. The perspective did. Someone finally started asking, where is all that energy going? And how can we recover it? We asked ourselves the same question we posed in Chapter 10. What else might we be overlooking in everyday life? And that's where we found ourselves stuck. We've applied the idea of harvesting energy from movement to roads. But honestly, we're still not certain where else the same principle could work. The floor of a crowded subway station, perhaps. The grandstands of a stadium. Or a pedestrian bridge that fills with people at the same time every day. Maybe the floor of a gym. Maybe the moving walkways inside an airport terminal. We don't know if the same thought crossed your mind while watching this, but the next time you look around, you may start noticing all the movement that's simply going to waste. When that maintenance worker checked the display one last time and closed the access panel, the vehicles passing overhead no longer looked like ordinary traffic. Each one looked like a small, silent contribution. Perhaps the greatest changes are the quietest ones, like a road that begins working silently, without anyone even noticing. Years from now, when a child asks, "Did roads really used to exist only for driving on?" That may no longer sound like a strange question. There are more projects we haven't shown you yet. Even the engineers working on them say, "This is crazy." We'll explore them in the next video. Turn on notifications and be among the first to see what's coming. Real problems, realistic solutions. G Projects.